In this part of our discussion of nervous tissue, we are going to discuss action potentials, which are traveling electrical currents. We will be looking at the electrophysiology of neurons and how signals are transmitted. An action potential is a more dramatic change in membrane potential produced where there's a high density of voltage-gated channels. The normal density of voltage-gated channels is approximately 75 channels per square micrometer. In the trigger zone, which is in the axon hillock, there can be up to 500 channels per micrometer. So in the resting state, the neuron is resting at -70 millivolts. Once we have a local depolarization that meets threshold, we get depolarization, or opening of the sodium channels. Repolarization is caused by potassium flowing out of the cell through voltage-gated potassium channels. We have a slight period of hyperpolarization where the potassium continues to leave the cell before we return to our resting state with our resting membrane potential. The steps of an action potential include the local graded potential created, and this causes some local depolarization. If the local depolarization reaches threshold, -55 millivolts, then it opens voltage-gated sodium channels. When these channels open, sodium enters, causing depolarization. Past 0 millivolts, the sodium channels close and stop depolarization. About this time, the slow potassium gates are going to fully open. These potassium gates are also voltage-gated, but much slower to open than the sodium gates. When these gates open, potassium can exit through these voltage-gated potassium channels and repolarize the cell. A negative overshoot produces hyperpolarization, and this is caused by excessive exiting of potassium. In this action potential, we have an electrode that's recording the membrane potential, and as the action potential moves past, we see a depolarization when the membrane gets more positive. That's the middle frame. And then after the action potential has passed, we see that the resting membrane potential returns after a short period of after a slight period of hyperpolarization. Notice that the action potential is only happening in one area of the membrane at a time. So it moves down the length of the membrane, creating an electrical current. An action potential is also called a spike. The characteristics of an action potential include following an all or none law. Either these voltage gates open or they don't. It is non-decremental. It does not get weaker with distance. It maintains the same level of depolarization as it moves along the axon. And action potentials are irreversible. Once it has started, it goes to completion at the axon terminal and cannot be stopped. These things are different from a local potential. This graph highlights the resting membrane potential in the purple areas when the voltage-gated sodium channels are closed and the voltage-gated potassium channels are closed. After a stimulus, depolarization to threshold will occur, as shown in the blue portion of the graph. Once we have reached threshold, voltage-gated sodium channels are going to open the activation gates. This is in the green period on the graph. Just after these activation gates open, the voltage-gated potassium channels will open and the sodium channels will close due to their inactivation gates. That's the yellow phase of the graph. The orange phase of the graph is where the voltage-gated potassium channels are still open, and the sodium channels have been reset to their resting state, with the activation gates closed and the inactivation gates open. The absolute refractory period includes the period where the sodium channels are open or when the sodium channels have inactivation gates that are closed. No stimulus can cause depolarization during this period. During the relative refractory period, that's shown in orange, it takes a larger than normal stimulus to create an action potential. This graph shows in detail what's happening during the different phases of an action potential. In the resting gate, the sodium channel has its activation gate closed and the inactivation gate open. During depolarization, the activation gate opens, and once we reach approximately 0 millivolts, the inactivation gate will close and the slow potassium voltage-gated channels will open and let potassium out of the cell. Then, when we get to the repolarization phase, we get back to our normal resting membrane potential. Both gates will reset to their resting state. Action potentials will only occur if the membrane potential reaches threshold. If the membrane potential does not reach threshold, no action potential will occur. If we have a very large stimulus, it will create multiple action potentials. This is how our neurons code for a strong signal. The refractory period is a period of resistance to stimulation. The absolute refractory period includes the time when the sodium gates are open or when the inactivation gates are closed. No stimulus can trigger an action potential. During the relative refractory period, which is as long as the potassium gates are open, only an especially strong stimulus will trigger a new action potential. Remember, just like the action potential is only occurring at a small patch of membrane at one time, the refractory period only occurs to a small patch of membrane at one time, and that membrane quickly recovers. In unmyelinated fibers without a myelin sheath, the threshold voltage in the trigger zone begins the impulse. The nerve signal or impulse is a chain reaction of sequential opening of voltage-gated sodium channels down the entire length of the axon. In unmyelinated fibers, the nerve signal travels at approximately 2 meters per second. You can see that as the sodium is let in, it triggers the voltage-gated channels right next to that initial stimulus to open and continue the action potential. Saltatory conduction occurs in myelinated fibers. These voltage-gated channels are concentrated in the node of Ranvier or the myelin sheath gap. So we have up to 12,000 per square micrometer in the gaps and fewer than 25 in the myelin covered regions. This means when those voltage-gated sodium channels in the myelin sheath gaps open, it lets in lots of sodium, and that sodium is able to quickly diffuse to the next node. So it appears as if the potential is jumping from node to node. This is called saltatory conduction. Saltatory means jumping, and the action potentials will jump from one node to the next. In continuous conduction, as we see on unmyelinated fibers, you can see that after 10 milliseconds, the sodium action potential has only moved a short distance, whereas in the myelinated neuron, you see that the sodium action potential has moved much farther. Saltatory conduction is quicker than continuous conduction. Some things that affect the speed of nerve signals include the diameter of the fiber, because large fibers have more surface area for signals. Myelin causes faster nerve signals, and warm temperatures cause faster nerve signals. The speed of the signal is related to the function of the signal. So slow signals supply the stomach and pupil, which can move slowly and not put us at risk. However, fast signals supply skeletal muscles and transport sensory signals for vision and balance. A fibers are large myelinated fibers and transmit nerve signals up to 130 meters per second. We find A fibers coming from somatic sensory neurons and in motor neurons. B fibers are small myelinated fibers which carry signals at 3 to 15 meters per second, and we find these in visceral sensory neurons and autonomic preganglionic motor neurons. C fibers are the slowest, and they are small and unmyelinated, and they travel at half to 2 meters per second. These are some somatic and visceral sensory neurons and autonomic postganglionic fibers. Next, we'll discuss how we get the signal across the synaptic cleft once it has arrived at the synaptic end ball.